Begin our study of piecewise functions. It's first important to go through and actually give a definition. It's an informal definition, but I'm going to say that a piecewise function is a function that is made up of pieces from other functions. Sometimes people refer to it as a Frankenstein function. Really, it's just lots of little pieces put together into a larger function. So if I look down here at example 1, I have a piecewise function f of x, and it's made up of two pieces, right there, 1 and 2. If you remember from Algebra 1, each of these are linear. Both of those guys, they form straight lines because they have slopes, and they have y-intercepts. Now, every part of my piecewise, actually every piecewise, has two of these sections for each function. It has the what I'm going to call x values, when do I use the function, and it has what I'm going to call the y values, what does the function do to x. So again, this is when do I use the function. For this first one, I only use the top function when I'm below 2. And then this tells me, well, what does it actually do to the x values? Well, it adds 2 on. And then looking at the other set, here I use this function when I'm 2 or above, and then it does something different to the x values. So every single piecewise part has these two sections, the x part and the y part. So if I want to evaluate a piecewise, for example here, I want to find f of -3. In other words, I want to plug -3 in. So I have to decide which of these sections does it fit in, because remember, these are my x values over here. So when I look at it a little more carefully, I see -3 is going to fit into that function up there. So to find f of -3, I go ahead and just take the first function and replace the x with -3. So that means my y value, because remember, this side is what gives me the y's, my y value is going to be -1. That's the output. So when I evaluate at -3, that's what I get. Get rid of a little of that stuff. Second example, I'm going to evaluate at a different place. In this case, I'm evaluating at -10. Positive 10, there we go. I'm at positive 10. So positive 10 fits into the bottom. X is greater than or equal to 2. So when I plug them into that function right there, I get f of 10 equals -1/2 times 10 plus 7. And a little bit of math, it's going to give me -5 plus 7, which is going to give me 2. So f of 10 is 2. So it's not too bad when we're looking at it and my values of x fall into one of these two distinct places. It gets a little trickier whenever I start looking at a value like f of 2. Because when I look right here, something special is happening at 2. That's where I'm switching from one function to the other. So I'm going to pay special attention up here to what we are going to call transition points. I have to be a little more careful with the transition points because I'm trying to decide what's going on. Which function do I plug it into? And this is going to mean a lot for me once I start graphing. So if I check out f of 2 and I look at my functions, I'm going to plug them into the bottom function because of that extra equal to right there. I'm greater than or equal to. So in this case, f of 2 equals -1/2 times 2 plus 7. So that's going to be 6. So when I evaluate a piecewise, I'm just determining which set do I plug it into. In this case, top or bottom, or I could have multiple sets. So evaluating is picking out where to plug it in. Graphing is a little bit. With graphing, what I need to do is I need to decide what kind of functions am I dealing with. So we already said each of these right here and right here are linear. So they have slopes and they have y-intercepts. And if I remember, how do I graph a linear function? I need 2 points to graph a linear function. So what I'm going to do is I'm going to look right here at this transition point, and I'm going to see for each of the functions what's actually happening at 2. Let me change my color slightly on the bottom one, make him red. I'm looking specifically at what's happening at 2. So in this case, I'm going to have 2 comma something, and I'm going to have, if I can get a red, 2 comma something. So now what I do is I take 2 and I plug it in because I want a y value. And remember, the left-hand side gives me y's. When I plug 2 in, I get out a 4. And if you notice something, he's going to be an open dot because he is just strictly less than. So I have an open dot at 2 comma 4. Now, in order to get another point on that graph, I am only allowed to live in the channel that is on that side because of that value right there, with x being less than 2. So what I'm going to do is I'm just going to pick any other ordered pair and plug it in that represents that channel there. So for example, I can take an x value of 1, and I can plug that in. I'm going to have 1 comma, plug it in, 3. And 1 comma 3 is up here. Now people always ask me, is it a closed or an open dot? The only time I have open dots is whenever I go through and look at a transition point. Other than that, they are just dots on my graph. So if I look at this, I know that my graph goes down like that because I have 2 points to represent it. I could choose any other point. I just happen to choose the one immediately beside it. If I look at the bottom function, take this 2 here and plug them in to my function, put the x in to get the y back out. If I put a 2 in, I get a 6. We actually already found that further down. And notice how he is a closed dot because of the equal to. So I go to 2 comma 6, put a closed dot. And according to my function, I'm only allowed to live on this side for the red one. I'm only allowed to be greater than or equal to 2. So I'm going to pick another x value in that channel, like 3, and I'm going to see what he gets. So go ahead and pick 3, comma, oh, 3 is not a great choice. Let's look ahead a little bit. If I take 3 and plug them in there, I'm going to get a fraction or a decimal. So I'm going to back it up a little bit, and I'm actually going to choose 4, because that'll work out to a nicer value. And I end up with 4 comma 5. You could do this with fractions and decimals, but I would rather that we learn to look ahead and see that that's not going to be good. So I graph 4 comma 5, and I complete my piecewise function. I've got the blue piece going to the left, the red piece going to the right, and notice how I did that by finding 2 ordered pairs. 2 ordered pairs for each function. So there's my first example of graphing a piecewise and evaluating a piecewise function. Example 2, it says to go through before graphing and determine the following values of the functions. So what I'm going to do, I'm just going to color code. We're going to call that blue, call that green, and we're going to call that red. And I'm going to look at where do I plug these things in. So for my first one, h negative 3. If you remember, this side gives me x's, this side gives me y's. So if I take negative 3, he's going to go into, let me get rid of that because it's not red. He's going to actually go into blue. There we go. He's going to go into the blue function. And there's a little confusion because people look here and say, when I plug it in, what do I get? Well, that value is 4 everywhere. No matter what I plug in for x, I get out 4. If I take the negative 2, I've got to be a little bit careful because he's one of my transition points. So he actually ends up being in the green because of that equal to right there. So when I plug in negative 2, I get negative 2 squared, which gives me positive 4 also for one of my answers. H of 0 is going to fall squarely in the green. So if I plug 0 in there, I'm going to get out 0. H of 1 is going to be another transition point for me. So I've got it checked. I see that there is where I'm equal to 1. So I'm going to put him into the red, which is times 1 plus 3, which is in fact 5. So there's my h of 1. H of 2 falls nice and squarely into the red, right in the middle of this guy here. So I'm going to end up getting 2 times 2 plus 3, which is 7. And lastly, h of 3, we've got a little bit of an issue because this function here goes up to 3 but does not include 3. So there is nowhere to plug 3 into my function. It doesn't fit into any of the 3 of my possible pieces. So I'm going to say 3 is not in the domain. He's not in the domain of my function. So there I go, going through and figuring out what all the different pieces of my piecewise look like. Next thing I'm going to do is I'm going to start graphing this. And if I look at the different function types, I know that that guy there is linear, that guy there is quadratic, that one right there is a little more difficult, and we'll talk about him when we get there. So I'm going to start at the bottom and do the red first. And I'm going to take the same approach I had before. I want to look at what happens in the channel he lives in. And the channel he lives in starts at 1, right there. And it goes up to 3 from right there. And notice how 1 is a closed dot. So I'm just going to put a little reminder there for myself. And 3 is an open dot. So if I plug those in, I can see what they're giving me. Put a 1 in. 2 times 1 plus 3 is 5. We found that. If I put a 3 in, 2 times 3 plus 3 is going to be 9. So it's actually as simple as going to 1, 5, closed dot, 3, 9, open dot, and since I know he's linear, I connect the dots. And that's the piece of my piecewise. Now you could find any of them in between. You could plug in 2 if you want and see where it's at. It doesn't matter, but you at least need the beginning and the ending, or 2 points in that section. I'm going to hop up to the top, and I'm going to do blue next. For the blue, he's -4, and that's closed. He ends at -2, and that's open. Now the tricky thing here is just realizing, like I said earlier, no matter what the x value is, my y is always going to be 4. So I can just go through and say he's at 4, and he's at 4 for his y value all the time. So when I graph it, -4, 4 is closed, and -2, 4 is open. So it actually gives me this little horizontal line segment. And if you remember, the equation y equals 4 would have been a horizontal line that I cut off at -4 and at -4. And last but not least, I need to look at my quadratic. And when I look at a quadratic, he's just a basic quadratic. So when I look at him, his vertex is at 0, 0, which falls into my channel. And then based on what I know about a quadratic, I know he goes through 1, 1, which is still in my channel. You just got to be careful because he's now an open dot. So he's an open dot at 1, 1. I know it goes through -1, 1. He's in my channel. And I know he goes through -2, 4. So if I plug in that -2, I get a 4 out. He's a closed dot. So watch what happens. I go -2, 4, and he actually fills in that dot right there. So I go through and graph the portion of my parabola that I have. So when I put this all together, I've got a piecewise function with 3 different pieces, a linear part in the red, a quadratic in the green, and a horizontal line in the blue. And I find all of those by just finding some points. The hardest one is the quadratic, but whenever you deal with those a little bit more, it gets a little bit easier to see where he is. Just focus on where is that vertex first. And the vertex is at 0, 0, and then just start graphing him until you get to the edges of your boundary. We'll continue in another one with the last example on this page and the idea of continuity.